Welcome. In this session, we'll learn the fundamental concept of Fourier analysis. Let's start. What is the fundamental concept behind Fourier analysis? Now, Fourier analysis simply says we can express any signal or waveform as a linear weighted sum of sinusoids. Means we can express any signal. Let's suppose if it's x of t, means if it's a continuous time signal, or x of m if it's a discrete time signal or sequence, we can express this as a linear weighted sum of sinusoids. So we can express this as a weighted sum of sinusoids. For example, if it's a continuous time signal, the like square wave, here triangular wave, or a speed signal, or any other waveform, or any other random waveform, we can express this as a weighted sum of sinusoids. Now, what do we mean by sinusoids here? Sinusoids means it can be sine omega t. Means taking a linear weighted sum of these sinusoids, we can get this signal, or this signal. Now, this sinusoids can also mean cos omega t, because we know sine omega t and cos omega t are one and the same signal. Only difference is the phase angle. Or we can use complex sinusoids like j omega t. We know this is equal to sum of this plus this. We know this is equal to sum of this plus. So we can use either these sinusoids, or this sinusoids. Sometimes we use both these sinusoids. You might have already seen it. So the point that I'm making here is we can express any signal x of t or x of n as a linear weighted sum of sinusoids, and the sinusoids can be either sine omega t, cos omega t, or even the complex exponential sinusoids. So let me illustrated. Let's suppose we have x of t, means the continuous time signal, taking a linear weighted sum of sinusoids is the Fourier analysis. Means combining different sinusoids with some frequency and amplitude, we can get x of t. Now the concept is x of t will be equal to like sine this a2 sine omega 2 into a3 sine omega 3 plus so on. So this is the concept behind, and there's Fourier analysis means taking the sum of different sinusoids with some amplitude and frequency. With some amplitude and frequency, we can express x of t as a linear sum of these sinusoids. This is the concept, and we can write this as a summation. So we can write it like sum ai sine omega I t, and the summation is running over I. So taking the sum of different sine waves with some amplitude and frequency, we can get that waveform. Means we can approximate that waveform. Now, the more number of these terms you take in this summation, the approximation will be better. Therefore, the signal you are approximating. For example, if you are approximating square wave, if you are approximating this square wave, the more number of terms you take here, the approximation will be better. Now, to illustrate this, let's suppose we want to approximate this square wave. Now, if you see the Fourier analysis of square wave, and you might have already seen that, that's not my point here. My point is to tell you what is the concept of Fourier analysis. So let me illustrate. Now, if you see this square wave, now we can express x of t, which is our square wave here. We can express this as a linear weighted sum of sinusoids. Now, if you see the what is the this Fourier analysis, or what is the how you this approximate this square wave. X of t is a square wave. How we can approximate it as sine waves? You will see that you can combine different sine waves. Let me use n instead. 4 by n pi sine n omega t. Well, omega is some frequency. Remember, omega is some frequency. So 4 by n pi sine omega t, where the summation is running over n. So in other words, this becomes like this 4 by pi sine omega t plus 4 by 3 pi. Remember, n is odd here. I forgot to mention n is odd. N is only odd. So this is sine 3 omega t plus 4 by 5 pi sine 5 omega t plus so on. Plus so on. So we can express this x of t, which is our square wave, almost image square. You can express it like this. That's how it is. Now you can take 4 by pi here common. And you can take 4 by pi here common and express it. Sine omega t plus 1 by 3 sine 3 omega t plus 1 by 5 sine 5 omega t plus 1 by 7 sine 7 omega t, and so on. We can do it like this, right? So this is how we express a square wave. Means we can approximate square wave by taking the, now remember, by taking the sum of the sinusoid. Now remember, this omega is the, there's some frequency. This will be determined by the square wave. What is the frequency of square wave? Now to illustrate this, let me show you this approximation of this square wave with this sine waves. Now see, in the first plot, this blue wave is our given square wave that we want to approximate, and in this plot we are using only one sine wave to approximate. You will see the approximation is very bad. The approximation is very bad, means we are expressing this square wave and using only one sine wave. Now, in the second waveform, you can check we are using two sine waves to approximate the square wave. In the third, we are using three. Then the approximation becomes better and better as we use more sine waves to approximate this. Means when we add more number of sine waves to this approximation, the approximation becomes better. You can see here the 5 sinusoids. Then when we use 10 sinusoids to approximate, means when we add 10 sinusoids to approximate the square wave, you will see the approximation is much better. Same way in this plot, we are using 15 sinusoids to approximate the square wave. Now you will see the approximation is now much better. And in this we are using 20 sinusoids, means we are combining 20 sinusoids to approximate the square wave, and you will see the approximation is much better. So we can approximate a square wave by taking the sum of different sine waves. In short, that is the whole idea here. Okay, so we can approximate any waveform as a linear sum of sinusoids. In short, that's the point. Now, before I proceed, please know what are these edges? What are these things here? Now, these things occur only in square wave. Means when we approximate a square wave with sinusoids, this occurs only in square wave. And this occurs at the edges where we have edges of the square wave. This occurs there. And what is this? This is termed as Gibbs phenomenon. This is not my topic here. This is termed as Gibbs phenomenon. This is not the point. Our goal here is how we can express a waveform as a linear sum of sinusoids. That was the point. Please don't pay attention to these edges. What are these edges? This occurs only in when we approximate square wave. I hope you have got the point. So the fundamental concept of this Fourier analysis that we can express any signal x of t as a weighted sum of sinusoids with some amplitude and frequency. And these sinusoids can be either sine waves, cosine waves, or complex exponentials. Or you can use both sine and cosine together. Why we use sine waves, why we use cosine waves, and why we use complex exponential. This gives rise to a different Fourier analysis that we shall learn later. I hope you have got the concept. The point in Fourier analysis is we can express any signal as a weighted sum of sinusoids. And here we have given the example of a square wave. Means we can approximate a square wave by taking the weighted sum of these sinusoids. And have a look, there are only odd terms here, means a square wave only contains odd frequencies. This is very important point for examination in interviews. The square wave only contains odd frequencies. It does not contain even frequencies. You can see there are only odd frequencies. And here omega is the fundamental frequency. And these are referred as harmonics. You might have already studied this. So sine omega t is the fundamental sinusoid, and these are the this harmonics of this fundamental sine wave. All right, I hope you got the concept. And in the next session, we'll learn why sinusoids. Why are we expressing? Why we want to express these waveforms in terms of sinusoids? What is so important about these sine waves? All right, let me end it here. In the next session, we'll do that.